the mechanics big problems again. I'm going to do this one in two parts because there are two problems here. So this first one, so I have M1, which is a box. It's compressed a spring with spring constant K, a distance D. It's going to be launched and have a collision with M2. It does tell you all this information. M1 has an inelastic collision with M2 and it rebounds with half its initial speed. Then M2 is going to slide over a rough surface and it's going to lose almost all its energy, meaning it's going to lose all its energy and just nudge M3. M3 is going to roll down the ramp and then be launched horizontally. And then it's going to stick in this massless cup. The collision itself is going to take away all the energy from the ball. And then this lever is going to release down here and let the whole thing rotate. Okay, kind of got this set up. I'm going to flip back and forth between the problems and the solution. So this is me finding V1 after the spring launch is all about conservation of energy. So this is 1 half kd squared, which is just 1 half kx squared, equals 1 half mv squared, and I find the velocity of the box. Okay, now we have a collision between M1 and M2. Then we're going to conserve momentum. So P1 equals P2. The original momentum is just this M1 V1, which we already know. And we know that it tells us that M1 is going to rebound with half of its speed. So this is a very key piece here, that has to be a negative in there. It's going to hit and go left. M2 then is going to go to the right, and we can figure out it's going to go to the right at exactly 1.3 meters per second. Then it's going to slide over a rough surface, and we're basically told it loses all of its energy. It's just going to nudge M3 to go down. So we're going to take all the kinetic energy that it had after the collision, and it's going to lose it due to heat. And so we can say that energy minus mu M2GD, which is the work done by friction, is going to be 0. We can figure out how far that rough surface must have been. Then M3 is going to roll down the ramp. Now, rolling down the ramp, we know that, because we understand moment of inertia and rotational energy now, that it has initial energy of mgh, and then it's going to convert that to both translational kinetic energy and rotational kinetic energy. So we're going to get a 1 half mv squared term and a 1 half I omega squared term. We know I for a ball is 2/5 mr squared, and that omega can be replaced by v over r, and then squared. So we can use that to find the velocity of the ball at the bottom of the ramp. Okay. Then we're going to get a horizontal launch. And we know for a horizontal launch, the velocity it's moving at, that 5.29, is simply the horizontal velocity. It's got no vertical velocity. So vertically, it's as if it was just dropped. So we can do our h equals 1 half gt squared to figure out the time. Then the horizontal distance is just the horizontal velocity, which doesn't change, right? Because the acceleration is only vertical in the air. So it's just that velocity of 5.29 times the time, and we can figure out how far then it would go. The torque on the rod, well, the torque on the rod is just going to be the force and the lever arm. Now, if you look at it, the force is just going to be mg, and the lever arm, well, that's just L over 2. Okay? So that's the torque. The initial angular acceleration caused by that torque, well, torque equals I alpha. You want to find alpha, you need a torque. We know the torque. The I is going to be, remember, the moment of inertia of a system is the sum of the parts. Always the sum. You're adding everything up. The board is 1/12 ml squared, because that's the moment of inertia of board, pivot at the beginning, at the middle. And then we have the point particle, which was m3, and that is mr squared, where its r is L over 2. And so it's that torque equals I alpha. So the original alpha, the original angular acceleration that the board and ball will be rotating after it falls down, it looks like 26.1 radians per second squared. The max angular velocity. Okay, so that we know is going to occur when the thing is fully rotated vertical. So this thing is going to hit, and then it's going to go down. So then it's going to look more like this, where the ball is going to be down here. We know that it's going to be rotating the fastest at that point. And so now we need an energy idea. Okay, so the energy at the beginning of this thing, well, what does it have? Well, it's not moving, so it simply has gravitational potential energy. And the board itself, well, that's the nice part here. The board itself is pivoted in the center. So when the board rotates, the board's center mass doesn't move. The only thing that's going to make this thing, have energy is the loss of energy, the loss of potential energy of M3. And so think about the height change. M3 is going to drop a height of L2. So that energy is going to cause a rotation. And we know then it's just 1/2 I omega squared. And we already knew I of the system. It's up here. And so then we gained our loss of potential energy converted to rotational energy, and we know that at the bottom we get that maximum. And again, omega is the angular velocity, rotational velocity, and that's in radians per second. Okay, so that is part one, and I'm going to stop this video now, and then we'll do a different video for the second problem.